expression. So what we're going to do here, find square roots, find cube roots, and do a lot of operations with radicals such as adding, subtracting, multiplying, and well, the division of radicals is actually the rationalizing of the denominators, which you have in a way in the other hand. Well, we are going to do a little bit of division of radicals, but that's more about the properties of radicals that we will do later in this review. These review notes. Okay, so finding square roots and principal square roots. So number one, what does it mean to find the square root? I mean, I'm pretty sure that if I ask you, oh, give me the square root of 36, you know what the square root of 36. What's the square root of 49? You know what the square root of 49 is. You what's the square root of 625? You can give it without even using the calculator. So I'm pretty sure you know the perfect squares, at least the first 15. And then you would jump to the square root of 20 maybe, and then the square root of 25. Those are numbers that you can get out of your head in the blink of an eye. However, well, let's define what a square root is. So for instance, well, the technical definition, or the formal definition rather, tells us that the number b is a square root of a if b squared equals to a. Well, that is, for instance, we asked ourselves what number, or numbers rather, squared equals to 49. All right? So what are those two numbers, by the way? 7? Just 7? And -7. So -7 and 7, right? So there's two numbers that if we square them, we should get the positive. We should get the number that we want to take the square root. So, and actually, principal square root, the principal square root is the positive one, right? That's the principal. We usually don't look at the negative. You will always take the positive one into consideration. A very important remark here, the square root of a negative number is not a real number. And you may have seen about them before, when you take the square root of -9. Well, what you do is take the square root of 9, which is 3, and then you multiply by the imaginary number represented by the letter I. Same if you have maybe the square root of -25, that also take the square root of 25, which is 5, and multiply by the imaginary unit. But for now, let's not take those into account. Actually, almost at the end of the semester, when we get to look at the representation of complex numbers in trigonometric and exponential form, we're going to do a big review of everything about complex numbers. How do we describe them? Where do they come from? And how are they related in trigonometric exponential form? You'll see later. But again, that's almost towards the end of the semester. All right, the properties of square roots. Every positive real number has two square roots, one positive and one negative, as we discussed earlier. All right, the square root of 0 equals to 0. And because 0 squared equals to also 0, right? And well, we use the symbol, which is called the radical sign, or the radical symbol, to denote the non-negative square root of a real number. All right? And again, the one that is the positive, the non-negative one, that's going to be considered the principal square root, because again, taking the square root of 49, that's going to give us, 7, right? However, there's really two numbers that if we square them, we get 49, and that's not just 7, it's also -7. But again, the positive one, it's the principal one. And the quantity inside, or the number, or the quantity, inside of the radical symbol, it's called the radicand. So a little bit more of vocabulary here. All right. So let's compute some square roots for now. Okay, what's the square root of 36? 6. Okay, 6. That's because 6 squared equals to 36. So again, we're looking for the number whose second power equals to the quantity inside of the radicand, that is 36. That's the meaning of finding the square root. So I know it's just, the square root, the first few perfect squares. All right, letter B. Let's go on the next page. So letter B, that's the square root of 9 over 16. Although later we're going to use properties of radicals to simplify this one in an easier way. In the meantime, let's think of what number squared equals to 9 over 16? 3 over 4, all right? So this will be 3 over 4 because 3 over 4 quantity squared equals to 9 over 16. Oh, careful with the decimals because the decimals can become a nightmare at times. Well, how do we deal with this with these decimals? Well, how about write this decimal in terms of a fraction? Recall that the number of digits that you have to the right of the decimal number tells you the number of zeros, which is the power of 10 you divide by. In other words, what am I trying to say? I'm going to write a big radical, and instead of 20.25, I'm going to write it as 25 divided by 100. In this case, because two decimal places, 2 zeros. Right? And well, that equals to, okay, what's that equal to? 0.0. Oh, well, no, not 0.05. 5 over 10. And that's because 5 over 10 quantity squared equals to 25 over 100, right? So again, think if you're having a hard time trying to compute a square root, always think of, okay, well, we're looking for a number whose second power equals to whatever the quantity we have inside of the radical symbol, that is the radicand. All right, let's put variables now. Let's see, the square root of x to the 6th power. Okay, if you know some properties of radicals, maybe you can answer that question. However, we're looking for what quantity squared equals to x to the 6th power. And what is that quantity here?
X to the power 3.
X to the power 3? Okay, that's because what do we do with the powers when we have the power of another power? Multiply them, right? So final answer, x to the 3rd power. And again, you might want to see the relation here. That is because x cubed to the 2nd power equals to x to the 6, right? And if you want to highlight this so you can see what are we really looking for, our target again is to, yes, the answer is the quantity whose second power equals to whatever we have inside of the radical. Yes?
Going back to C.
Sure.
If you simplify the 25 over 100 to 1/4, would that still be right?
Yes, that'd still be right. Yep. And in fact, we would get a way simpler number, right? Well, that's what we're going to do later when we look at the properties like the product rule and quotient rule, and to simplify that first before using the properties. That is correct. And in fact, yes, 25 over 4 indeed is 1/4, right? Yep. Oh, letter E. Okay, that's a combination of a letter and an exponent. Now, here we're looking for a quantity whose second power equals to 9x to the 12th power. What is that quantity?
3x to the power 6.
3x to the power 6? I agree. 3x to the power of 6. All right, and again, that's because 3x to the power 6. Here, again, the exponent 2 affects both the 3 and the power 6. 3 squared equals to 9, and power of another power, multiply the powers, that's 6 times 2, which equals to 12. All right. Okay, what about, what's next? Let's see, cube roots. Okay, so for cube roots, we're going to answer a very similar question. So rather than finding the quantity whose square is whatever quantity is inside of the radical symbol. This time we're going to look for the number whose third power is a quantity inside of the radical. And if we and you can follow the same pattern for the root. Well, what power is what number whose fourth power is the number inside of the radicand. If you want to find the 17th root, what quantity or number raised to the 17th power equals whatever quantity is inside of the radical. So we just follow the same pattern. All right, let's talk about cube roots. The same technical definition, the formal definition, that is the number b is a cube root of a if b cubed equals to a. For instance, we ask ourselves, what quantity cubed equals to 27? 3. All right, that's because 3 cubed equals to 27. In the same way we did it with squares, but now we're doing it with cubes. And again, in this case, in comparison with the square roots, the cube root of a negative number, we can take it. We can take the cube root of a negative number as opposed to the square root of a negative number, which is not a real number. And well, let's see. For instance, okay, let me do the cube root of negative 8. All right. What's the cube root of negative 8? In other words, what number cubed equals to negative 8? Negative 2, all right? That's because this guy right here is negative 2 times negative 2 times negative 2. So, in this case, we will be multiplying 3 negatives. Negative times a negative is positive, times a negative is negative 8. However, what if I wanted to think of the same process for the square root of negative 4? All right? Is there a number whose square equals to negative 4? Oh, okay. What about negative 2? Okay, let me do negative 2. Okay, let's think of it. That means in this case, well, negative 2 times negative 2. Oh, but hold on, that's going to give us a positive 4, not a negative 2. So it's impossible to multiply a negative number, an even number of times and get a negative number. So this equation, that statement, it's impossible, but it's possible only for odd powers, because when we multiply a negative number an odd number of times, it's still possible to get a negative as opposed to an even number. So in this case, the cube root can be obtained for a negative number, the 5th root, the 7th root, the 9th root, all the odd roots as opposed to the square root, the 4th root, the 6th root, the 8th root, etc., all the even roots, right? However, like I mentioned before, we're just going to limit to evaluate square roots and 4 root, but I think there might be some 4 root out there, but anyway. All right, let's compute some of them. How about after a 10-minute break? So let's evaluate some cube roots. A cube root of negative 64, that is, what number raised to the third power equals to negative 64? Negative 4, right? Negative 4. So negative 4 is the answer. What number cubed equals to 8 over 125? And I hear 2 over 5. That number, 2 over 5, equals, it's going to be the answer, because raise the 2 to the third power, that's going to give us the 8, and raise the 5 to the third power, that's going to give us the 125. Let's introduce variables to them. Okay, what quantity to the third power equals to x to the 6th this time? X squared. Okay, so later we will see a way quicker rule to compute this value. You'll see when we change this radical notation into rational exponent notation. All right. Let's see. What about the next one? This one involves, again, not just a variable, but also a numerical coefficient at the same time. All right, so again, here we're looking for the quantity whose third power equals to 27, or 27x to the fifth power. All right.
3x to the
So number one, the coefficient 3 cubed, that's 27. Now x to what power equals to 15? 5, all right? Final answer then, 3x to the 15. 2x to the 5. All right? Okay, the expression a raised to the 1 over n. All right, what about it? So now here we're going to go back and forth between the radical notation and rational exponent notation. That's another notation that we're going to use a lot later when we get to the trigonometry part, the core part of the course. All right, so for n being an integer, usually these indices are integers like, well, when we have a radical with nothing inside, or no number in between this angular part of it, well, that's an invisible too, unless you have something like cube root or fifth root or seventh root, etc. All right. So now here is the thing. When you have the expression quantity, not just a number, it could be a number times a variable raised to the 1 over n. The denominator of the rational exponent is going to be the index of the radical. Again, let me highlight this. So the denominator of the rational exponent is going to be the index of the radical. All right. So, and again, keep in mind that if the number is even, like the square root, like the fourth root, the sixth root, then that root of an even index, it's not going to be a real number. That's what gives rise to the set of complex numbers. And again, we're going to discuss those later in the semester. All right. Let's have a look at example number 3. Write each expression in radical notation, and then, if possible, evaluate the expression and round to the nearest hundred if necessary, if appropriate. All right, let's have a look at this. Okay, 9 to raised to the 1/2. Well, let's go ahead and write it as a radical. Well, and again, I would like to highlight the denominator because that denominator will be the index of the radical. So in this case, well, that'll be square root of 9. You might want to write a 2, but again, you don't need to write that 2 because whenever we have that radical symbol that without a number in there, that actually involves, that implies a square root, all right? And well, if possible, evaluate the expression, and what's the square root of 9? That's a 3, all right? And we no longer have to go because 3 squared equals to 9. I think we got the gist of it. We got the concept already. Oh yeah, there's going to be a weird index right here again. So, let's see. Number 1, let's highlight the denominator of the rational exponent, in this case of 5. That means that'll be the index. And well, that'll be the fifth root of 18. Make sure to have the 5 over here. All right, and I'm going to later. I will discuss a little more about the position of the index. Now, well, in this case, there's no integer I can think of that if we raise it to the fifth power gives us an 18. So in this case, we're going to round it to the nearest hundred as appropriate. Now, let me open the calculator so I can. So I can show you how to, give me a second, quit. Let me clear everything. Well, you have the radical symbol, that's for the second, well, no, not second, I don't want a second, just, oh yeah, second square root. of 9, for instance, and that's going to give us the square root of 9. However, for other roots, your graphing calculator should be equipped with this fifth operator here, which is x radical symbol. That's to evaluate roots that are beyond the cube root or the square root. Here we have a dedicated a function to compute the cube root, but if you want other roots, you need to go about this symbol here. So let's go about number 5, and that's going to give us a couple of blanks in here. That'll be, well, in this case we want the fifth root of what's that? The number 18, which is the number in the radicand. And in this case, well, that's going to give us a decimal number of 1.7862. However, they're asking us to, what's that? To round our results to the nearest, what is that? 100. That is, how many decimal places is the nearest 100? 2 decimal places. What would be the result rounded to 2 decimal places then? 1.78. All right. So this is approximately 1.78. All right. Okay, let's work with variables here. Okay, again, the denominator of the fraction of the rational exponent rather will be the index of the radical rather, and that'll be fourth root of x. And lastly, be careful here when we have a combination of 3x raised to the 1/7. I mean a combination, a product between what is that? A variable and a number. So in this case, notice also how this 3x is inside parentheses. So we need to make sure to have the whole radical 3x and the index of the radical, which is 7. That's going to be our index here. Be careful, because what if we have instead 3x to the 1/7? This is not the same as that expression we had over here. So in this case, what is it? It's only the 1/7 is only affecting the x, but not the 3, and that's a whole different result. All right. So parentheses matter. So be careful, if there's no parentheses, well, it's going to look like this instead. Right? All right. Let's move on to the next and see what we get. Oh yeah, that's actually the next example. Oh, I thought I didn't have it. Okay. How about? Yep. And pretty easy to do. We just change the colors. All right. So again, the moral here is just the denominator is the index of the radical. Now, what if the expression, like in the next page, well, for the first exercises we did before, we had that exponent, the numerator of the rational exponent, to be a 1, but it could be something else. It could be something other than 1. All right. Well, it turns out that in this case, it's still going to be the same thing. In this case, the denominator of the rational exponent will be the index of the radical. And check this out. The numerator of the rational exponent m, either there's a couple of ways to express it. Either remains in the exponent of the radicand, inside of the radical, or outside as parentheses, with parentheses. And in fact, well, maybe we will use one or the other depending on the number that we're computing. And it's important to take this one into consideration for, well, we'll see about different case scenarios. And again, the same remark that if we have an even index, we cannot take the even root of a negative number, right? Because that's not a real number. All right, let's see this in action right here. Okay, 4 raised to the 3 halves. What about it? Again, the denominator will be the index of the radical. So, and okay, let me show you the 2 ways to express this. And actually, I'm going to have a look at both quantities and show you why one is going to be easier than the other one. Typically, check this out. Typically, this is hard to compute, but this one is easy to compute. I'll show you why is this. Okay, so number 1, let's use the same property of radicals to rewrite this number that is raised to a rational exponent, that is the square root of a quantity 4 to the 3rd power, which is also the square root of 4, however, the whole thing raised to the 3rd power outside. Now, let's have a look at this. Which one do you think is easier to compute? Oh, well, actually, I already told you which one is the harder and why. But, well, let's have a look at why it's hard. So, which one do you prefer to compute, the first one or the second one? Why is that?
Because we find the square root of 4 easier.
And what is the square root of 4 in this case? 2. And then you can cube that number 2 afterwards, and that's going to give us? Okay, so that's a 2 raised to the 3rd power, which equals to 8. Now, if we compute the hard one, which is fine. Okay, what is 4 raised to the 3rd power?
64.
And then take the square root of 64. Well, for this one, it's a nice and easy number. But what if we have something like, I don't know, bigger numbers? So you don't, what I'm trying to say here is, you don't want to get something really big that can potentially be harder to simplify. Instead, simplify first, get something easy, and then square it or cube it or raise it to the 5th in accordance with whatever we have. All right. All right, so that's one example. What about negative 27 raised to the 2/3? And again, in this case, we can compute this negative because the index or the denominator of the rational exponent, it's a negative number. I mean, it's an odd number, not a negative, so it's odd. All right, so again, if we go about the radical notation, that is the cube root of negative 27 raised to the 2nd power. Oh, this one is going to be a really good example about why that is hard to compute. All right? Okay, so what is 27 squared? I mean, without calculator, so let's say you are in a quiz or an exam and you are not allowed to use a calculator. So, do you see how this one is hard to compute? You will have to do it by hand, 27 times 27, do the multiplication by hand, and then, you will have to take the cube root of a big number. And do you know cube roots of those big numbers? I think the highest perfect power might be, what's that? The 625, the 25 square, right? The one that we can get out of our heads easily. So no, that's why we go not the hard one, but the easy one. That is the cube root of negative 27, and then raise it to the 2nd power. All right? How about we take the cube root of 27? Isn't that really easy to compute? And what is that? Negative 3. Mm-hmm. Negative 3 raised to the 2nd power, positive 9. All right? So again, let me hard. Yes. You should still get the same result. That is correct. All right. Now here is the thing. What I'm trying to do here is to, in a way, guide you through the way that when you're dealing with this kind of quantities, in the middle of calculations for other bigger problems, you don't have to spend time doing this in the calculator, raising it to the second and take the cube root of it. Rather, to be more practical, so you can see, oh, there's an easier way. I think let's make it smaller and then make it bigger rather than make it bigger and deal with a bigger problem instead. But I mean, in the end, it's up to you how you get that. Okay, let me do in the calculator, that is parentheses, negative 27. What is that? Squared, right? That's a big number, all right? 729. Now it's the, what is that? The cube root? Yes, second. No, not second. That's whoops. Let me clear. So what is that? Math. Let me do number 4. That's the cube root of 729, and that equals to 9. You should get the same result. However, I'd rather go the easy way rather than the hard way, but it works the same way. What about this one? 1/9 raised to the 3/2. Number 1. Let's take let's write it as a square root of 1/9 squared, or rather cubed. And well, you don't want to raise the 1/9 cubed, because again, 9 cubed, I believe that's going to take us back to the 729, the number. So instead, take the square root of 1/9 first, whatever you get, cube it. And what's the square root of 1/9? What is that? 1/3 or 1/3. Cube it. Isn't that a lot easier? Notice how I'm not even using a calculator to compute this. So that's the path I'm trying to guide you through. 1 cubed, what equals to 1? 3 cubed equals to 27. All right. Okay, for the next ones, all we're going to do is just write them in terms of radicals, because well, there's nothing really to simplify, just like A through C. Now, and again, the denominator of the rational exponent is the index of the radical. That is a 5th root of the quantity 4x minus 1 to the 3rd power. And when it comes to algebraic expressions, we usually keep it with exponent inside of the radical. By the way, I mean the one that looks like the hard way. I mean, we're not going to compute anything right now. We're just rewriting the algebraic expression. And the reason why we don't write it the other way, it's because, check this out. It's a lot of grouping symbols, right? And I think looks more practical or more clean, rather, the hard way in a way than the easier way in a way. All right? So let's keep going. The expression a to the negative m over n. So it's very similar to what we had over here. However, it's going to have a negative exponent. So now we're not just going to be dealing with rational exponents, but also we're going to add the negative sign. And all we're going to do is send this quantity to the denominator with positive exponents. And whatever we do in examples A through C, do it in the denominator. That's all it is. All right? Or if we had, check this out, there's a part B to this that I didn't type, that I'd rather had to write instead. What if a to the negative m over n? Well, then move it to the numerator with positive exponent. We can have in it either one. So let's see. And again, same advice here. If your index of the radical is even, then we cannot take that root of a negative number. All right, let's see. Write each expression using radical notation. Then evaluate the expression by hand whenever possible. All right, let's go ahead and do that 16 to the negative 3/4. That'll be, first of all, let's rewrite that negative exponent as a positive exponent by sending this quantity to the denominator. That is 1/16 to the 3/4. All right? And then we're going to use the same property as we did before, but now we're doing this in the denominator. That'll be 1 over the 4th root of 16 to the 3rd power. All right? And again, without using a calculator, do you want to raise that 16 to the 3rd power to get a really big number? It's going to take a good minute to go because you would have to multiply 16 times 16 by hand to get a 3-digit number, and then multiply it again by 16 to get maybe a 4-digit number. And then you would have to think of finding the 4th root of that big number, which is not practical. We can't do that. That's not a feasible task. Instead, again, instead of doing the hard way, we're going to go the easier version. That's the 4th root of 16, the whole thing raised to the 3rd power. And I think it's a lot easier to take the square root of 16, which is going to be a smaller number, and then cube it, and that's going to nail it here. All right, what's the 4th root of 16? In other words, what quantity to the 4th power equals to 16? 2. 1 over 2 to the 3rd power, 1 over 8. All right. For letter B, negative 27 raised to the negative 2/3. So number one, let's write the negative exponent as positive by sending it down to the denominator. But in this case, make sure to keep the negative if the number inside of the parentheses. All right. Now let's see. So now we're going to go to the radical notation, that is negative 27 under the radical of index 3, quantity squared, and then go the easy way instead. And write it like this. So now we're going to compute the square root of negative 27. What's that number? Negative 3 raised to the 2nd power in the denominator should give a 1/9. All right. Okay, example number 6. So now we're going to do, in a way we're going to do this backwards. So now we have these radical expressions with powers inside of the radical, but now they're asking us to write them in terms of rational exponents, and preferably if negative, that's also fine. All right, again, keep in mind that in the same way that the denominator of a rational exponent is the index, thinking of it backwards, the index of the radical is going to be the denominator. So all we do here is x, 2, 7 is the numerator, rather 3 is the numerator, and the denominator is 7. In this case, let me highlight it so you can see how it's the denominator, really the index of this radical. All right. For letter B, we're going to do the same operation first in the denominator, and then whatever we get, we're going to send it to the numerator with negative exponent. And again, no number in front of the radical symbol, or rather in the corner. That means it's a square root, so the index will be 2. So in this case, that's 1 over b to the 3/2. However, we don't want to keep it in the denominator. We move it to the numerator with negative exponent, right? Same here. The index is 5. That's going to be the denominator of the rational exponent. That is x minus 1 raised to the 2/5. And again, the 5, this 5 right here comes from the index 5. And last but not least, one more. Okay, be careful here, because right here there's an invisible 1 power. So that's going to leave us with a squared minus b squared raised to the 1/4. And if you want to keep highlighting that index, which is the denominator of the rational exponent, keep doing it so. So, well, these are kind of short type of exercises. All we're getting familiar with is to rewrite a radical expression in terms of rational exponent, potentially negative rational exponent, depending if those denominators contain the radicals in this case. All right. Okay, so let's keep working on more radicals. The product rule for radical expressions. Well, in other words, whenever we have two radicals multiplying together, what we're going to do, we're going to write one single radical with the product of the radicands. In other words, the product of two radicals is the radical of a product. And we're going to see this in action with a few examples here. So, for instance, multiply each radical expression. So, what do we have? The square root of 3 times the square root of 5. All we're going to do, write this as the square root of 3 times 5. Simplify the number. 3 times 5 equals to 15. And if the number were a perfect square, we'll simplify it. But in this case, since the number 15 is not a perfect square, then we don't simplify it any further. All right? And what about, in this case, the square root of 21 times the square root of x? That's just the square root of 21 times x, which is 21x. And in this case, the number 21 is not a perfect square, and x is itself not another not perfect square. So we just leave it like this. And this idea of radicals, again, it's going to work for pretty much your favorite index, whether this is a square root, cube root, 4 root, etc. So in this case, the cube root of the product of two cube roots, it's going to be the cube root of the product of the numbers, 4 times 2. And in this case, 4 times 2 equals to 8. However, in comparison with the examples we did for A and B, this number has a perfect cube root because the number whose cube is 8 equals to 2. All right. So that's the what's that? Combining radicals via multiplication. What about simplifying the nth roots? Okay, in essence, we're going to do the backwards process of that property that we did here. For instance, for example, this example 1, we did this property this way. The product of the radicals equals the radical of the products. In the simplification of radical expressions, we're going to use this, but backwards, all right? And I'll show you how we're going to do this. Well, simplifying radicals and roots, those could be square roots, cube roots, for root your favorite index. Number 1. We're going to determine the largest perfect nth power factor of the radicand. And number 2, use the product rule to factor out and simplify that perfect nth power. For instance, we're going to use, because we're going to do this a lot later when we get to computing values of trigonometric functions. We will have to simplify these radicals, and no, we're not going to leave them in terms of decimals. We will actually leave them in exact form, and we need to be able to simplify these radicals. For instance, the square root of 50. What's the square root of 50? Well, if we think about it, is there a number whose square equals 50? Well, there's one close that is a perfect square. It's 1 unit less. It's 49. But no, it's not the case, unfortunately. However, what we're going to do here is factor out that number 50 into two products in a way that one of those factors is a perfect square. Okay, any ideas on how to factor the number 50? 2 times 25, all right? Is any of those two factors a perfect square? Which one? What's the root of 25? Okay, so this is what we're going to do. We're going to break down this number 50, and I'm going to write the perfect square first. 25 times 2, all right? And well, usually, the first when I usually teach it for the first time, I like highlighting with a good color, with green, all those numbers that will be the perfect square that we will be able to take the square root of. All right, that's going to be the 25. But now we have the radical of a product. In the same way we have the radical of a product, we're going to go backwards and write it as the product of two radicals instead. All right, that'll be the square root of 25 times the square root of 2. And just evaluate the square root of the perfect square. In this case, what's the square root of 25 again?
5.
And the square root of 2, it's just the square root of 2. So that'll be 5 times the square root of 2. And final answer. All right? That will be an exact answer. So again, later in the trigonometry chapters, when we compute values of the trigonometric functions, we will be obtaining results like this, like the square root of 50 that we need to further simplify, because MATLAB is very picky about it. You cannot input the square root of 50. It's going to ask you to simplify, and it's going to ask you to leave it in exact form. That is, this is exact form, unless otherwise stated, for which you're asked to simplify or to input your results as decimals. All right? Okay, let's look at another example. What about the square root of 24? And this one might be a little tricky. That's because there's a couple of ways to factor the number 24. However, it is the index what is going to tell us what to do. In this case, the invisible index is 2. That is, look for perfect squares. All right? Because we want to take the perfect square root. Now, there's a bunch of ways to factor out the number 24. Any ideas?
8 and 3.
8 and 3. Okay, 8 and 3, but now between 8 and 3, are any of those factors a perfect square?
4 and 6.
4 and 6. Okay, I like that 4 and 6. Okay, so the square root of 4 times the square root of 6. All right? And let's write this as a product of two radicals, square root of 4 times the square root of 6. Compute the square root of 4, which in this case equals to 2, times the square root of 6. Just leave it like this because there's no integer whose second power equals to 6. And that's final answer. All right. Let's have a look at the next exercise, which looks very similar except for a little subtlety here. While for letter B, we were looking for the square root. For letter C, we're looking for the cube root. And that's going to take us back to your input here, Corey. So in this case, this time, look for perfect cubes this time. All right? That's what this index is instructing us to do. Look for perfect cubes. All right, and again, we can discuss different ways to factor out the number 24, like 6 times 4, which work for letter B. Now, 4 times 6 or 6 times 4 is not going to work for letter C because neither 4 nor 6 are perfect cubes. However, in this case, it's going to be 8 times 3, because in this case, A, it's a perfect cube, and it doesn't matter if the 3 is not. All right, there's another way to write down the 24, like I believe it's 2 times 12, right? But that's for sure not going to work for neither B or C because neither 2 nor 12 are perfect squares. So now let's go backwards and write the product, the radical of the product, as the product of the two radicals. And the cube root of 8, which is
2.
2, and cube root of 3. All right, guys. Let me stop real quick and talk about a potential issue when writing these radical quantities. Make sure to have that index to be in between this space. And the reason to this is because very often times we are in a hurry and writing a lot of numbers. We're doing the homework on MyMathLab. We're using scratch paper. We want to do it real quick, and we tend to write something like this and looks like this. And when I read this, to me it's not very clear what about these 3. Well, let me make it a little bigger because I've seen it before, and a lot of students have gotten this result. And so in the middle of the calculation, sometimes students, instead of having this index, to be represented as index, what they do is either multiply 2 times 3, which equals 6 times the square root of 3, which I don't know what happened here. By a mathematical miracle here, the cube root suddenly just became a square root, which doesn't make sense at all, right? That's one issue. Or simply reporting it as 23 square root of 3. And again, by another mathematical miracle here, the cube root, the index 3, simply became an index 2. So again, notice how you might have noticed how am I writing this tiny index number in the spacing between the radical symbol, so it actually looks like a radical symbol. Try to be as neat as possible when it comes to that. All right, this way you don't get different results. All right, letter D. What about the square root of 72? Let's think about that one. Actually, all right, for this example in particular, well, the bigger the numbers they get, these numbers get even more possibilities for factoring them. All right, that is, well, what about the number 72? What are ways to factor the number 72? Okay, let's list them.
236.
2 times 36, all right? What else? 8 and 9. Or 9 times 8. I would like to write the perfect square first. All right? And is there another possibility?
18 and 4.
18 and 4, potentially, yes. 4 times 18. All right? And I believe 12 and 6, right? 12 times 6. So do you see how there's a bunch of ways to do this? Okay, let's go back to the very beginning of this. In this case, determine the largest perfect nth power. And out of all these ways to factor, well, yes, this is a perfect nth power, rather a perfect square. This is also a perfect square. This is also a perfect square. However, we're going to go with the first one because the largest perfect square that factored the number 30, the number 72, is this 36 in here. And I'll show you why are we going to do this. So that's the square root of 36 times 2. That equals to the square root of 36 times the square root of 2. And the square root of 36, which is 6 root of 2. And that's going to take us to the result pretty much in a couple of steps, as opposed to actually there's nothing wrong with doing the other way. Check this out. Let me show you this on the side. Now, the square root of 72 equals the square root of 9 times 8. Write it as a product of two radicals, square root of 9, square root of 8. And well, let's factor out the square root of 9, which is 3. However, this square root of 8 can be further simplified to number 1. 3 root of 4 times 2, which equals 3 root of 4 times root of 2. And the square root of 4 equals to 2 and root of 2, which equals 6 root of 2. Actually, it's the same result. However, the fact that we go with the highest, with the largest of the nth powers, that's in a way that we can do this problem in a more efficient way using a lot less steps as opposed to doing it with the 9 times 8. Do you see how many steps is? 1, 2, 3, 4, 5, 6, 7 steps as opposed to just 3 steps. So we're saving a lot of work by looking for the largest power in this case. All right. And all right, let's go back. So let's have a look at simplifying more radicals. All right, using this product rule for radicals. However, we're gonna use it backwards as we have done for letters A through D. All right, for letter E. Now we're going to combine not just numbers, but also powers of x. All right. And here is the deal with the powers of x. Well, we can already see that we can simplify the square root of 25, which equals to 5. All right? So that's going to be, well, we'll find out. However, how about we break down those, how we break down the 25, no, not the 25. Okay, the 25, we know it's a perfect square, all right? However, is the quantity x cubed a perfect square? And it's not a perfect square because, well, this will rely on the following. For instance, like, let me do some examples on the side. Let's say the square root of x to the 4th. Is this a perfect square? It is. It is because if we go back to rational exponent notation, 4 divided by 2 equals to 2. And when we no longer have those radicals, right? But what about x to the 5th power? X to the 5th power, that is x to the 5 over 2. In this case, the 5 doesn't go into 2 evenly, so that's why x to the 5th is not a perfect square. How about x to the, what's that? X to the 3rd power, that is x to the 3 over 2, and because 3 doesn't go into 2 evenly, well, it's not going to be a perfect cube. However, we will break down that x to the cube, x to the 3rd power into a product of a perfect square, that is x squared times x, right? So we're using backwards laws of exponents so we can find this perfect square root. And now we're going to notice how in this case we have 3 factors. That's going to be the square root of 25, the square root of x squared times the square root of x. Now the square root of 25, which is going to be 5, the square root of x, which is x to the 2 divided by 2, and then the square root of x, which is simply the square root of x, and well, that's going to be 5x square root of x after simplifying all the perfect squares. All right, so in other words, okay, to make it even easier, well, this one might be a little weird to do, so let's move on to the next example, letter F. The cube root of 54x to the 6 y to the 8th power. Well, how are we going to compute that one? Well, let's see. So notice how in order to determine whether these powers of x are perfect squares, what we did is divide the power by the index, and if it goes evenly, well, then it is a perfect square. Like x to the 4 is a perfect square because then the exponent 4 is divisible by the index and we get a nice integer. X to the 5th is not, because 5 doesn't go into 2 evenly. X cubed is not a perfect square because 3 doesn't go into 2 evenly. So number 1, here we're going to look for cube roots. Now, is 54 a perfect cube, by the way? Okay, can we break down the number 54 in a way that one of the factors is a perfect cube? What are those numbers then?
2 and 27.
27 and 2, right? Okay, now here is the trick. Is 6 divisible by 3? Then x to the 6th power is a perfect cube. Let me just leave it the way it is. X to the 6th, right? And is 8 divisible by 3? Now we need to play with the powers of 8. Okay, what number smaller than 8 is divisible by 3? 6. Okay, so I'm going to write this as y to the 6 again. Also to the 6th power. Times y to the remaining power. 6 plus 2 makes up the 8, right? Now here's what I would like to do. I'm going to group. Let me highlight all the perfect cubes in here. And I'm gonna write them together. And I'm gonna go like the cube root of 27, x to the 6, y to the 6, and I'm gonna write the 2y squared right after. I'm grouping the perfect cubes first. All right? So, and then I'm going to use the properties of radicals. I can take the cube root of 27, the cube root of 27, that equals to, what's that? 3. What is the cube root of x to the 6? In other words, what is 6 divided by 3? 2, x squared. 6 over 3 for the y, that's also y squared. And then we're done simplifying the perfect cubes. And that'll be the cube root of 2y squared. All right? The square root of x to the 11, y to the 17, x and z to the 8. Now the question here is, we need to make sure that the exponents are evenly divisible by the number implied in the index, and in this case, well, there's nothing here that means 2. Is 11 divisible by 2? So we need to break up this x to the 11 as a product of something whose power is divisible and something that is not. What about 17? 17 divisible by 2? What about 8? Well, that one is a perfect square. Well, so I would like to break this up like x to the, okay, what integer smaller than 11 is divisible by 2? 10, x to the 10th times x to the 1 to the first power. We don't need to write that one. What about 17?
16.
X to the, y to the 16 times y. And z to the 8 is z to the 8. All right? I'm going to highlight all the perfect squares. All right? That is all the variables whose actual powers are divisible by the index 2 and keep everything inside. All right? That is the square root. Okay, let me put them together first. X to the 10th, y to the 16, and z to the 8 times xy, which is the remaining factors that do not have perfect squares, that are not perfect squares rather. And I'm going to write a couple of radicals. Number one with x to the 10th, y to the 16th, z to the 8th, and another times square root of xy. And well, here is where we divide 10 by 2, 16 by 2, and 8 by 2. That's going to give us x to the 5th, y to the 8th, and z to the 4th. And that's times the square root of xy. Right? Final answer. And again, make sure to have that 4 to look like the power of c. Be careful with your notation, because if you write it somehow this way, that it's a little bit ambiguous and it's not very clear to me, and it's not going to be very clear for you actually, if it is the power of z or the index of the radical. So try to be as neat as possible when writing these radicals. All right, let's see what's next. All right. Oh, how about the same example but with cubes? Okay, so notice how letter H is very similar to letter G. In fact, we have the same variables x, y, and z, and even raised to the exact same powers, 11, 17, and 8. However, what makes the whole difference it's the index. While here we have a square root, here we're gonna have on letter H we're gonna have a cube root, and that's gonna change the game a lot, because now we're gonna be looking for powers that are divisible by 3, not by 2. And here is where we check them out. Is 11 divisible by 3?
No.
Okay, we need to break it up in a way that one power is divisible by 3. Okay, what number smaller than 11 is divisible by 3? 9. All right. So we will be left with 2 powers of them to make up for the 11. What about y? Y equals 16, or no, 17 first. And is 17 divisible by 3? So what number then it's smaller than 17 is? 15. So that is 15, and I will be needing 2 more to complete the 17. What about z to the 8? Z to the 6 times z squared. All right. Group the perfect cubes in this case. All right. Highlight the index if it works. As a reminder that we are looking for perfect cubes inside of the radical. So that'll be cube root of x to the 9th, y to the 15, z to the 6, and just write down times x squared, y squared, z squared. All right. So only so we will break this up as two radicals again. Cube root of the cube roots of the perfect cubes rather. And that's x squared, y squared, z squared. All right. Well, let's simplify 9 divided by 3. That's x cubed, 3. 15 divided by 3, that's 5. And 6 divided by 3, that's 2. Times the cube root. And again, see how we have a combination of the exponents 2 from the z and the 3, which is the index. Make sure to write it in the correct space so it's clear that the 2 is the exponent of the z and the 3 is the index of the radical. So x squared, y squared, z squared. All right. So you can think of this as these powers of x. These x squared, y squared, and z squared are not powerful enough to get out of jail, if you think, because what's the price? The price, you have to bribe the gatekeeper here. You need to pay 3, but how many do you have here? 2. You need 1 more. You don't have them? Well, you're still in jail until you can get out of there, right? Okay. So let's see. So that was the product rule in action. First, we go for by multiplying two radicals. The product of the radicals is the radical of the product, and if it's possible to simplify it, well, go for it. But otherwise, we did the reverse now, which is we're given a big radical, and we were looking to work our way for all those factors inside to find their way out of the radical, out of Yale, if you will. And that's actually dictated by the index of the radical. That's going to tell us what to do. You know, if we have an index 2, look for perfects. Where you have an index 3, you're looking for perfect cubes, etc. Again. Now we're going to do the quotient rule, and as I mentioned before, we were going to find an easier way to compute this, but not anymore by the definition. Earlier we did something like this, like, oh, what number squared equals to 25 over 49? Well, if you're still with the definition, you can already guess the answer. However, this time The radical of a quotient is the quotient of two radicals, that is the square root of 25 over 49, that's the square root of 25 divided by the square root of 49. And in this case, we happen to have two perfect squares, two really nice numbers, that is 5 and 7. All right? For letter B, same thing. We have the radical of a quotient, that is going to be the quotient of two radicals, in other words, square root of x over the square root of 9. That's the square root of x, which is simply the square root of x. However, the square root of 9 is a nice number that can be simplified to 3. In some cases in which the radical in the denominator is not a perfect square, well, that's something called rationalizing the denominator, which we will do in the second part of the previous handout. I gave you the one. I decided to take another detour to do this first, and then we'll get there. All right? Same thing if we have a different index. The cube root of the numerator 8 divided by the cube root of 27, which is the denominator. Now, in this case, well, we have a couple of nice numbers in which the cube root is a perfect, the cube root of 8 is a nice number equals to 2, and the cube root of 27, which equals to 3. In fact, I think this was one of the examples when we were looking at the definition, but now we're using a property of radicals, that is the quotient rule of radicals. All right, for examples, letter A through C, we have one big radical that we rewrite as a quotient of two radicals and simplify each individually. Now, this time we have a quotient between two radicals. However, how about the square root of 20? The square root of 20, it's not going to be a perfect root. And the square root of 5, well, it's also not a perfect. The number 5 is not a perfect square as well. So in this case, write it as one single quotient, 20 over 5. How about we divide 20 by 5, which equals to 4? And isn't that a nice perfect square? That's a 2. All right. Same with the next one. The next one could be a little tricky. So, especially with the way we are going to denote this 2 in the denominator. However, we're going to focus on the quotient between the two radicals, which will be, this 2 in the denominator, let me write it as 1 over 2, as 1/2 times the square root of 50 x over the square root of 2. That way you don't get confused about the 2 that it's by itself at the very end. And now we're going to use the quotient rule for radicals. The quotient of two radicals equals the radical of a quotient. And the quotient is 50x over 2. And we can simplify a little bit. Of course, how about 50 divided by 2? That equals to 25. And in the same way we did with simplification of radicals, using the product property but backwards, 25 is a perfect square. However, x is not a perfect square, again, because it's not powerful enough to go out of the radical. The index, the gatekeeper, is asking for a 2, but this x has only a 1. It's not powerful enough, so that's going to stay in. Only the 25 is going to go out. That's 1/2 times 5. Root of x, and you may not want to leave it like this. How about instead 5/2 root of x? And that's our final answer here. All right, let's see. So that's the quotient rule in action. Do we have more on the next page? That's about it. Okay. Adding and subtracting like radicals. Well, what we're going to do next is just combine like terms. I mean, in a nutshell, it's combining like terms. For instance, okay, let me give you a couple of examples in which we do the combining like terms. For instance, 3x plus 5x plus 5y rather, minus 7x plus 3y. Well, what we do to combine like terms, combine the x terms with the x terms and the y terms with the y terms. That is 3x minus 7x, that's a negative 4x, 5y plus 3y, that equals 8y. All right? How about something like 3x squared y minus 5xy squared plus 7x squared y. Okay, so which ones are the like terms in this case? So only the terms that contain x squared y? Well, then you know what? Let me add one more. Minus 2xy squared. So we can have a nice combination. In this case, well, let me group via highlighting the like terms to distinguish them from the unlike terms. Notice I'm highlighting the terms containing an x squared y with green and the terms containing xy squared with a different color, just so we can in the end focus on combining the coefficients. And how do we know that these are like terms? Because the ones in green, for instance, okay, they have the same variables, x and y. Well, these are also x's and y. However, for the green ones, we have to have the same x, the same power for x and the same power for y. And what about the yellow ones? That's x to the first and x to the first, and y to the second, y to the second. So all we do is simply combine the coefficients. That's going to be, okay, 3 plus 7, that's a 10x squared y. And negative 5 minus 2 minus 7x y squared. And that's the answer for combining those two. Again, like terms are terms that contain the same variables and raised to the same powers. How are we going to extend this idea or this concept to radicals? Well, like radicals are radicals that contain the same index, that is, they're all square roots or all cube roots, etc., and contain the same quantity inside of the radical, that is, the radicand. All right, let's have a look at this. So, if possible, add the expressions and simplify. What do we have? 2 square root of 5 plus 7 square root of 5. Do we have like radicals here? Do they have the same index?
Yes.
Do they have the same radicand? They do. So all we do is simply 2 plus 7, 9, 9 square root of 5. This is like doing 2x plus 7x equals 9x, if you will. But in this case, the x is replaced with the root of 5. And we don't simplify the root of 5. Actually, we leave it in exact form, unless we have something that can be simplified further. But for now, let's keep it with something that can be simplified. All right, letter B. 3 cube root of 10 plus 7 cube root of 10 minus 5 cube root of 10. Can we simplify this to one single radical? Do we have the same index for all radicals? Do they have the same quantity inside? Yes, then they're like radicals. So all we do is 3 plus 7, which is 10 minus 5, that equals to 5 cube root of 10. All right? Now, let's combine not just numerical values inside of the radical, but also variable terms as well. Now, here is the thing. Do we have the same index for these radicals? Do we have the same quantity inside of those radicals? So they're like terms for sure. All we do, 5 plus 9, 14 square root of 2x. All right? What about letter D and letters D and E? Well, letter D. Let's do one at a time. Letter E. Letter D, rather. I mean, the first term is missing the radical, so we cannot combine an integer with a radical. So in this case, this is simply equal to itself, 12 plus 2 root of 6. There's nothing here to do. Letter E, square root of 3 plus square root of 10. Can we combine those two together? Why not?
They're not the same radical.
They're not the same the radicand, the quantity inside of the radical, right? So in this case, simply root of 3 plus root of 10. And then we write this down, common mistake. Common mistake in algebra, root of 3 plus root of 10. It's the combined root of 3 plus 10, which equals to root of 13. That's not what we do. We only combine the coefficients. 5 plus 9 equals to 14. 3 plus 7 minus 5 equals to 5. Only the coefficients, but not the quantities inside of the radical. This common mistake is very similar to that when we're working with powers. For instance, when we're working with something that looks like 3x squared plus 5x to the 7. Well, 3 plus 5 equals to 8. And x to the 2 plus 7 equals to 9. So we don't combine, we don't add up the powers. And in fact, actually, these do not have any like terms. That's actually the most simplified one. All right. So the same thing occurs with radicals. Again, we need to have the same index, which we have here, the same index. However, we don't have the same radicands. That is the quantity inside of the radical. All right. Adding and subtracting on like radicals. Okay, here we go. So we want to simplify this expression. 4 square root of 3 plus square root of 12 plus or minus square root of 27. All right, here is the thing. Yes, we have the same index of the radical. They're all square roots. I agree with that. However, we don't have the same index. I mean, we don't have the same radical. We have a 3, we have a 12, and we have a 27. However, because they're asking us to add or subtract and then simplify, that means there's a way around and put them together rather. And I think up to this point, after simplifying a lot of radicals using the product rule one way and vice versa, I think you can see the pattern of what we're going to do, because there is a root of 3 that can be potentially be here and there, right? So how about we repeat the process of simplifying the square root of 12 and simplifying the square root of 27 in a way that we break down those numbers 12 and 27 in a way that one of them is a perfect square and the other one is not. All right. Is there a way to break up the number 12? So one of the factors is a perfect square. So 4 root of 3. That is, okay, plus square root of 4 times 3. All right? And then what about the negative? What about the number, the 27? Yep. Let me write the perfect square first. Now, do you see what's going on? Do you see what's going to happen? Root of 3. Somehow I'm going to have a root of 3. Somehow I'm going to have a root of 3. So after playing with the numbers, simplifying them, we will be able to turn these unlike radicals into like radicals. All right, let's find the square root of 4, which equals to, is that a 2? 2 root of 3. And the square root of 9, which is 3 root of 3. All right? What do you think of this now? Can we combine these radicals together? 4 plus 2?
6.
Minus 3?
3.
3 square root of 3. That's one example. All right? And of course, with the pattern will be the same. We may get to do the same with cube roots, with other indices, or, oh yeah, the next one is a cube root. All right, now, Well, actually, I think we did that one earlier, the cube root of 24. So let's think of it again. Is there a way, in this case, to factor out the number 24 in a way that one of the factors is a perfect cube in this case, not a perfect square like before? And we need to do this because even though we have the same index of 3, we don't have the same number inside of the radical. That means that's the reason why we can't combine them together. All right, what about that 24? What factor of 24 is a perfect cube? 8 and 3, right? 8 and 3. So that is going to be cube root of 8 times 3 plus 2 times cube root of 3. All right, take out the cube root of 3. That equals to 2 because 2 cubed equals to 8. Cube root of, again, check the position of the index. And now we just rewrote at least we rewrote the first radical in a way that it has not only the same index, but also the same radicand. And we can combine them together now. What is 2 plus 2? And that's it, right? 4 cube root of 3. All right.